Hi, chemistry. Hello, how are you? I miss you. Let's talk about gas laws, because I know you have that test coming up, and it'll be on your final. Gas laws are actually very easy. They're pretty straightforward, so the places they try to trick you when they, being chemistry teachers like me, where they try to trick you is like in definitions and things, or trying to make the problems complicated when really they can't be that complicated. The first thing I want to point out is that do not confuse gas laws, which is about the state of matter gas, like solid, liquid, gas, with gasoline. That's just bad branding, okay? Gas, as in gasoline, is a liquid form of a certain hydrocarbon, which we use to fuel our cars. It's a fossil fuel, okay? Unless you have a Tesla, then I guess you don't. Or any of the electric cars. Anyway, gasoline is a fossil fuel. We call it gas because we like nicknames, right? We like to shorten things. But gas has a solid, a liquid, and a gaseous form of itself. The gasoline has a liquid gas form, as a liquid form, which is what we put in our cars, and it has a gaseous form, or a gas form, or gas state, which is when you smell gasoline at a, oh my god, at a gas station. That's when the gases start to evaporate really quickly, okay? Because gasoline has a very low vaporization point, and so it goes into gaseous form very easily. The molecules start moving fast enough that they can escape the liquid form. That's kinetic molecular theory. And so that's what you smell at a gasoline. That's also, those gas molecules in gaseous form are also very flammable, which is why they say do not smoke cigarettes at a gas station. Don't go in and out of your car at a gas station, because what you're doing is you're providing an energy source, like the cigarette light, the cigarette fire. There we go. You're breathing fire, or the static electricity of moving in and out of your car, which could, if the the gasoline gas molecules have permeated the air enough, if there's been enough evaporation, and then you have a spark of some kind, it could explode. Okay, so not great. Don't do that. But again, the thing that people usually don't realize either till the end or never is that when we talk about gases, we are not talking about gasoline. Okay? Check. But when we talk about gases, that's often where we start talking about the kinetic molecular theory. So kinetic molecular theory is not just for gases, it's about all particles in matter. The idea being that the more energy you add to particles, the faster they move, and as they start moving faster, they start interacting more, okay? Because it's like, think about little kids given sugar, okay? So a bunch of little kids just hanging out, maybe they don't move so much. You give them a little bit of sugar, a little bit of energy, they start bouncing around, they start moving more, they start hitting the walls and start banging into each other. That's like gas molecules, okay? So that's like molecules that are in the gaseous state. They have more energy than a solid or a liquid. And so according to kinetic molecular theory, they are more likely to hit each other and possibly react. But we don't talk about the gas reactions because that doesn't work with our math. So just know it does increase pressure, though, because pressure is all about how many molecules are hitting something, except for like social pressure. That's different, okay? But we're talking about chemical pressure. We're talking about how much stuff is hitting a wall or hitting a container edge, or a container side. And so gases have higher pressure than solids and liquids, often because they fill up the entire chamber, and not just the bottom like a solid does, or the X and Y directions like a liquid does. Like I have a carbonated beverage here, and the liquid is filling both the X and the Y direction, so it's filling not just in this direction but also in this direction, but it's not filling in this direction because it's a liquid. But the carbonation, which is a gas that is put into carbonated beverages when it's really, really cold, because it's a lot easier to manipulate gases when they're cold because they have less energy, so they're less likely to escape. Okay, kinetic molecular theory. Those molecules are gases within a liquid, the rest of the fluid, and so, not fluid, the rest of the liquid, and so the gas particles are what are escaping. That's also what makes you burp, okay, because the gas particles leave your stomach and then kind of build up in your esophagus until you let it out as a burp, okay? Okay, cool. Okay, so there's actually, remember, so the kinetic molecular theory says that molecules are always moving, they move faster when there's more energy present. So temperature is actually a measure of how fast molecules are moving. It's basically a speed test for molecules. We call it heat. It's not technically heat. Oh, don't get weird. But the idea is that the faster a molecule moves, the more energy is present, the more liquid or fluid. Okay, the more fluid that molecule is, or that substance is. So you'll notice there's a difference between fluids and liquids. So a liquid is a state of matter, solid, liquid, gas, right? Fluid describes anything that can flow. So that actually describes liquids and gases, maybe plasmas, but they get weird. So it's hard to experiment with plasmas. So in this kind of chemistry, we don't talk about it too much. But remember, there's actually 5 states of matter. You've got Einstein's condensate, which says, okay, if kinetic molecular theory says the more energy you add to something, the faster the molecules are moving. Well, there's got to be a point where you take away all of that energy and the molecules stop moving. And so Einstein considered this. He said this has to be possible, and so it was named after him, Einstein's condensate. So the idea being it's something as condensed, right? It's where all molecular motion stops. The particles have even less energy, are more cold than solids. That's mostly theoretical, but people are trying really hard to find this state. It's kind of like finding a black hole. It's a very big major point in science. But the thing is, stuff gets really weird as motion slows down that much. Like, it starts acting in ways that we do not expect and that we could never have suspected. But that's, if you're interested in this is definitely something to consider in future chemistry classes. Stuff gets weird. You have to work under mountains in order to work on Einstein's condensates, because just the cosmic particles that are able to get through our atmosphere are enough to interact with something and give it energy, and then you no longer have a condensate because there's energy in it, right? I could go on. Let's move on instead. So remember, a solid there's a little bit of motion. So even in a perfect solid, like, I don't know what a perfect solid is. Like, I have this metal ruler. Okay, it's a solid. It does not change shape unless I make it change shape, because the molecules are moving so slowly, they're basically just vibing next to each other, that the overall shape of it doesn't change. Okay. The first thing I thought of was, if I melt it, it'll change, but that's adding energy, right? That's causing it to go into the fluid state, liquid state a bit more than solid state. Okay. I could break it. That's a physical change. Remember, these are all physical changes, by the way, not chemical. It's adding energy. I could break it, but again, that's not the molecule's fault. That's something I did to it. On the other hand, a liquid, like my liquid in here, it's got a bit more energy. There's more motion of those molecules. So while the ruler, or a solid, has a defined shape and volume, can't change. It's a ruler. No, it's a ruler. Okay. Liquids have a bit more flow to them because they are a fluid. They have a defined volume, but they don't have a defined shape. Okay. So they fill their containers in the XY direction. They don't just like fill like sideways. They're going to fill it all. Okay. But they don't go up. They can only go side to side, front to back. Okay, we add a little bit more energy, and depending on the substance, the amount of energy you have to add changes. Water is actually one of the hardest substances to heat up. The reason why we say, if you're making pasta, you wait till the water boils, is because that tells us that the water is hot enough to freeze dry our pasta. Okay, that all it is a measure of temperature. It's not the boiling itself that causes your pasta to be, your instant ramen to become real ramen. We know it's a hot enough temperature that we know our food will cook properly at that point. Okay. Because what's happening in a boiling situation is the number of gas molecules that are leaving, because the gases are moving around a bit more. Crazy, right? Move it, and they're in a liquid every time. Okay, so let's think about if you're sweating, right? Think about what cools you down when you're really hot. It's not just sweating, because then you're just covered in hot water. Okay, it's the fact that as air goes over you, it pulls away the hottest molecules, because they're the ones moving the most, and they're the most likely to get to the surface of your skin, and they're the ones that are going to be picked up by the wind and taken away. Okay, so the same thing happens in any liquid. As it starts to heat up, the more active molecules they're more likely to get to the surface of the liquid and then leave and escape. And boiling happens when you have more things escaping than you do coming in. And so technically gasoline that we use in our cars, it's not really boiling, but it's evaporating enough that you get a lot of, it's very easy to get gasoline to evaporate into its gaseous form. Water, on the other hand, it's really hard to, you'll get some evaporation all the time, but it's really hard to make a lot of it evaporate because it has such a lot of internal bonding. We talked about it. Don't worry too much about it. What do I want you to worry about, or should you worry about? Know that gases have no defined shape or volume. They fill a container in all directions, okay? So if you think about a balloon has certain structural integrity so that you blow a fluid into it, or blow fluid, yeah, I mean, it's not too bad. You blow a gas into it and it's going to fill the shape of the balloon. But really the gas wants to go everywhere. It wants to be free. It wants to go everywhere, which is why when you pop a balloon, it's so quick to make a crazy noise, right? Because the structural integrity has been breached and the gas then can escape very rapidly. Because gas has such high pressure, it's going to want to do that if it can. Finally, we have plasma. Do not confuse with blood plasma. That's a case just like gas and gasoline, where it's just the same name used in the wrong context. It's actually a fluid. Plasma in your blood plasma is a fluid component of your blood. It's anything in your blood that's not a cell, or, it's the liquid component of your blood is called plasma. In this case, if we're talking about kinetic molecular theory and phases of matter, plasma is actually the highest, the most energy-rich form of matter. So if you have a gas and you add even more energy to it, so more and more energy, oh my god! It's like in the sun, where you have a lot of fusion happening, and as fusion is happening, you have molecules smashing into each other, and they release a whole bunch of energy, and they're moving so fast, they're moving faster than gases, that light starts to be created. Okay, so electrons are sheared off, light particles happen, and they're very hot. So that's why the sun exists. That's why the sun exists, actually, is because fusion and gravity are balancing each other, and you get this, like, all these gases moving so quick, and it releases so much energy that gets to the planet and gives our plants food and keeps us from getting too depressed, usually. Okay, so go outside if you're feeling crappy. If it's safe. Okay, so we also have, if you have fluorescent light bulbs instead of like LED light bulbs, or if you have the ones in classrooms, the long ones in classrooms, those are also heating up the part of the gas inside of that fluorescent bulb enough that it's creating a plasma, and so light is created. Okay, in other light bulbs, it just heats up the metal enough that the metal creates a light. It's so hot that a light is created. It's slightly different. It's just microwaves, fluorescent bulbs, and the sun are the most common places where you see plasma created. I do not recommend actually doing it, but you can go online and look up grapes in a microwave, like grapes like you eat, and they create a form of plasma for some reason. There's some molecule in their skin that will create plasma. It could explode and kill your microwave, so, watch out for that, but it is fun to watch someone else do it, because of that plasma form. Okay, but back to gases. So gases have these very certain characteristics, which makes sense if you think about them. Sorry, I just got a text. Can't pay attention. So they make sense if you think about them. So gases expand to fill their chambers, so which is good because that's what happens when you breathe. Your diaphragm contracts. It's a muscle that sits underneath your lungs. It contracts. It causes your lungs to open up. And then because your lungs are opening up, air rushes in. So if you think about the idea of taking a deep breath, you think you're shoving air in your mouth. No, it's actually, it feels like you're doing it at your mouth, but you're actually doing it at your diaphragm. So if you've ever been a singer or played an instrument, like a reed or a brass instrument, they say to inhale from your diaphragm, and that allows your diaphragm to take up, to push down more further and let your lungs fill up more, and then as your lungs are filling up more and that vacuum is created, you suck in more air. So take a deep breath and realize you're not actually taking a deep breath. You're contracting your diaphragm so your lungs get bigger. It's just harder to say that. It's also like saying bite down. We don't bite down. Our mandible, which is on top, it doesn't move. This is our maxilla. Our mandible on the bottom, it moves. So we don't bite down, we bite up. So, fun fact. Do you miss me yet? Okay, so, I missed y'all. Okay, so gases expand to fill a chamber in all directions, and the reason why is because of it's explained by kinetic molecular theory. which is that the molecules have so much energy, they actually escape gravity, because gravity is actually a really wimpy force. And so the gaseous molecules have so much energy, they literally bounce away from everything. Okay? They bounce into each other, they bounce into walls, they bounce into everything. Okay? So that's expansion. So because of this, so think about, again, our kids in an area, they've got a lot of sugar. You want them to go outside if they've got a lot of sugar in them, because they're starting to increase the pressure in the classroom by bouncing into things, and they're starting to spread out. So, okay, so if things are spreading out, remember that's expansion, that's also decreasing the density, because density is how much stuff is in a certain area. It's the amount of grams in a certain volume. And so sorry, text. Don't look at your phone while you're teaching, Noel. And so if a gas is expanding to fill more and more of its chamber, then they're spreading out more, and so they have they have more basically holes in the matter, and so there's more space between the molecules, which gives them less density. That's why something like helium will float. Okay, because a helium balloon will float because the helium is so spread out and the molecules are so light that it actually is light enough to lift the balloon material. Okay, so you don't see that in stuff like air we breathe out, because the air we breathe out is just heavy enough that the balloon, if you fill a balloon with it, it's too heavy for the balloon to lift. The balloon material itself plus the air is too heavy to escape gravity, but helium does. What? Huh? Oh yeah, water's weird. Water, as things spread out, you get lower density. But in water, there's a point where as it becomes more and more solid, it actually starts to spread out, which is weird. That's why ice floats. That's why life can exist, even though there might be ice on top of a river, not LA. There can still be fish underneath because ice floats. Okay, so gases. By the way, is it 1S or 2S's? American tradition says it's 2S's. European tradition says it's 1S. Yeah, that's whatever. So I apparently did both. Okay. Gases are fluids. I mentioned this. That means they move slowly. They flow is what I'm trying to say. So you might say, but Miss Null, what if I have like a big bag of rice and I like pour it and it flows nicely? Okay, that's fine. But what you're doing there is the individual particles themselves are not flowing. A collection of the rice grains are flowing, not the individual particles. In gases, the individual particles or molecules can flow, okay? Thank goodness, because that's how air can get into our lungs so we can breathe. Thanks, air. Thanks, evolution. Okay? Fabulous. What does this have to do with kinetic molecular theory? It's the same idea. If you have more energy, we know it's a good metaphor for life. If you have more energy, you can do more things. Okay, so solid molecules just sit there vibing. Liquid molecules start to like get moving a little bit, but gases can move all over the place. And so because they can move all over the place, it's very easy to make them move places. Like if you're breathing, if you have weather systems being pushed around the world, etc. Okay. Again, and these are all very closely related. Because gases have low density, there's all that extra empty space in between the molecules because they're bouncing off each other. You can compress them. So think if you blow up a balloon and then you start squishing it, there's a point where you can like squish it into a smaller point depending on how much gas you put in it, and then you let it go and it gets bigger again. Okay? If you've ever taken a water bottle and like breathed into it and then squished it, and then you open it and steam comes out, some people say it's smoke. It's not smoke, it's steam. What you've done is you've actually increased the pressure of the bottle when you squish it, and then you decrease it, and the water vapor that's in here if you do it fast enough, the water vapor doesn't have a chance to go back into its from the gaseous form by the high pressure, into the liquid form that happens when you let it go again, and so you see it as steam instead. Okay? What does that have to do with kinetic molecular theory? It all has to do with the fact that as molecules of a substance get more energy, they can move more, okay? And because they're moving more, there's more space for them to be squished, to be compressed. All right, so diffusion. I like to look at this picture when I'm thinking about diffusion. So diffusion is you put some molecules in one space, and because of what's called Brownian motion or random motion of particles, which is the more energy you have, the more Brownian motion. It all comes back to kinetic molecular theory. So because molecules are bouncing, if you watch one, you'll see they bounce off each other, and they bounce off the walls, and then you see they go in a straight line until they hit something, and then they bounce. Okay, so that's diffusion. It's just random movement of molecules until the molecules have filled up their whole space. You may remember from biology what's called the high... Oh, whoop, that's not it. Do you remember... What have I done? I don't need to do this. Oh, y'all, I'm so tired. Okay, go. Okay. You may or may not remember from biology. We don't have to talk about it too much. But the idea of moving from high to low concentration. That is diffusion. So the idea being, okay, that like, let's say someone sprays Axe body spray or some perfume, and you're way on the other side of the room, but they're going crazy. They're just loving themselves with that Axe body spray. Well, now, so that's like in this GIF where all the particles start together. Okay, but because they're gases, they're moving quickly, they're bouncing off each other, and they're trying to fill the space, and the space is whatever room you're in. Okay, and so they move from high concentration, which is where you start, to low concentration, which is where they've expanded, they've spread out, they've decreased density. Okay, so that is diffusion. We talk about this a lot in biology. Because that's how a lot of stuff works in biology, through water. But it's also very, very important with gases as well. Okay. All right. So so this GIF could be a liquid or a gas. For me, when I'm talking about liquids, I feel like I'm looking down into a chamber where I've just put like a drop of dye, and you can see it start to spread out. But this could be a gas if you think about it in 3 dimensions. Okay. Okay. So you might look at this and say, actually, like in some parts it doesn't look like it's evenly spread out after a certain point, but the idea is that the average is that they're spread out as much as possible by the time diffusion ends. Okay. All right, this is not to be confused with effusion, which is just diffusion through a small hole, okay? If you've ever watched, oh my god, what is that show where like somebody gets in a chamber and there's a bunch of dollar bills flying everywhere and they have to catch the dollar bills and it's so hard and you're like, I could totally do that. But what's really happening is that they're being flown around at a very high energy, okay? And your hands are very small and the particles, the dollar bills, are very small, so it's hard to make contact. Okay, but for some reason with gases, they can do this through what's called effusion. So effusion is just diffusion through a small hole. Okay, so the idea being that if you have a vacuum force on one side of that small hole, the gas particles will start coming out pretty regularly. So it kind of overcomes that idea of its random motion, but it's random motion with a force pulling in one direction, and so the gases can go out of that direction. Okay. Again, this is how we breathe, so yay, we like it, because we're creating a vacuum with our diaphragm contracting, opens up our lungs, air can come in. Thanks, evolution. How does this relate to kinetic molecular theory? This doesn't work with liquids so much. I mean, it does if it's below the place, the surface of the liquid. You get a steady flow. But this is actually, it happens more than you would expect. It's more than random motion can be attributed to random motion. It's just a property of gases that if you have one little place where the gas can be drawn, it's very easy for it to be drawn, even though technically it should be harder because they're all spread out all over the place. Okay? And it's because of kinetic molecular theory that those particles are spread out because they're very high energy. Okay, that's our characteristics. So, anytime you mention the speed of molecules and the randomness of the molecules moving, that is kinetic molecular theory, okay? So we talked about in each of the definitions. Okay, so let's talk about what's the difference between an ideal and a real gas. Okay, so it's like your ideal soulmate versus your real soulmate, okay? So the idea being you may have so it's... there are certain characteristics that you can attribute to almost all gases in certain conditions, but it makes the math weird if we try to be too realistic with it, which makes it hard to teach in chemistry. So we like to only deal with ideal gases. So the idea of an ideal gas is that they don't react with other molecules, no other molecules. So if you think about it, that doesn't make sense, but we just pretend it does, and it's fine because it makes it easier. Okay? They always behave exactly the same way at any temperature, pressure, or volume, which we know also is not what happens in real conditions. And they, what was the other one? They always move in a straight line until they hit something and bounce. Okay, so they basically act like little marbles. Let me add that. Okay, and they always move in a straight line until bouncing off of something. Off of something. All right. Now you might say, why does that matter? But that is assuming that there's no influence by gravity or other forces. Usually we're all under the same influence of gravity, and so it doesn't matter. But in some cases, like when you're boiling water at a higher altitude, there's a lot less gas molecules in the atmosphere at a high altitude, so the water boils faster, okay? But it's not as hot. Okay, and remember, boiling just tells us when it's okay to heat our pasta on average. And so if you're boiling something at a high altitude, like if you go to Big Bear, if you're cooking something, you have to let it boil a little bit longer than you would normally before you put your food in, okay, because it's not hot enough yet. Okay, real gases often interact with specific molecules. Again, thanks, because that's how we breathe. And they react differently at extreme temperatures and pressures, okay? So it may be at certain temperatures, certain pressures, they start to move faster or slower, whatever. Which makes sense because obviously at a extreme low temperature, we're not dealing with gases anymore. It's become a liquid again. Okay. But in ideal gases, assume that all the math works, the temperature and pressure do not affect behavior of gases, and they do not react with anything, okay? So how do we talk about gases? We talk about gases with pressure. It's one of the ways. And so we have different ways to talk about pressure because at the same time in, I don't know, 1700s, there were people in England, Germany, France, somewhere else probably. They were all studying gases because someone had just invented the hot air balloon. And they were like, holy shit, look at this thing, you can go in the air with this! And remember, this happened long before airplanes, okay? So if you don't know what a hot air balloon is, let me show you. Air balloon. That's this. And so the idea is it's a balloon big enough, you fill it with enough gas, helium usually, and look at this. What's this doing? That's heating it up. That's making the gas molecules move faster. If the gas molecules move faster, they spread out more. The more they're spread out, the less dense it is, and the less trapped by gravity it is, and so it can move up. Okay, so that's called the buoyant force. So that's why you add heat to the air inside of a hot air balloon. Oh, is it even helium? I don't know. It might just be air. I don't know enough about hot air balloons, but I can tell you that people who studied hot air balloons were obsessed with hot air balloons. And so what they noticed, each one of them noticed something different, okay? So, I mean, I'm skipping ahead a little bit, but one of them noticed that if you heat up the air, it expands. So volume and temperature are related. Some of them notice if you heat up the air, pressure goes up. Some of them notice, like with the water bottle when you squish it, that, and this is also how clouds form, that if you increase the pressure on something, gases, the volume decreases, okay, because you're literally squishing it, and so pressure goes up. So as volume decreases, pressure increases. And you also can change states in that form, but we're not going to talk about it. And all of this was happening because they were looking at hot air balloons, and they were obsessed, and they were adorable and ridiculous. And so they all decided, like, people knew about pressure before. They had these weird barometers. So a barometer measures pressure. And so they had these weird tubes. Barometer. So the reason why it's called millimeters Hg is because they had these tubes, this guy, where they would fill these tubes with mercury, which is Hg, and when they filled it with mercury, the air pressure would push on the one side of it because it was open to pressure, and that if it was high pressure, then it would push on that mercury, and then the difference in the size, the difference in where it originally was and where it goes to is your pressure, okay? And so they called it millimeters of mercury. Awesome naming, y'all. By the way, if pressure goes down, that means it's about to rain. So fun fact. Or you're about to have a tornado. So we don't have those in LA, so that's good. But in the Midwest, they have the right conditions so that like suddenly you have a really hot air mass coming in, gases, and you have a really cold air mass coming in, and then there's nothing around it to stop them from just smashing into each other. And the hot one needs to, like, it's going underneath, but the cold one, it's on top, but actually the cold needs to be on the bottom because cold stuff sinks because molecules are getting closer together. Kinetic molecular theory. And so the hot one wants to go up because it's more spread out, it's less dense because the molecules are moving faster because of kinetic molecular theory. And so in a tornado, what's happening is those two air masses are basically fighting over who gets to be on top, because the hot one should be on top, but the cold one, maybe it got pushed on top instead. This happens sometimes, especially in the Midwest. And so you get, as they're trying to move, you get that cyclonic activity and you get tornadoes, which are very scary. My mom, when I was a little child, used to hide me away in the bathtub when there was a tornado. One came down our street once, and she'd just go stand on the porch and be like, oh, that's so pretty. Because she was a crazy artist. And so tornadoes can like literally go fast. The air moves fast enough in a tornado, and this is where gases get kind of scary, in a tornado or a hurricane, that they can literally take a piece of paper and smash it through concrete. And so, not great. Don't stand outside near a tornado. If you've ever seen Twister, you see the cow go flying. That happens. Don't be outside in that. Okay, back to studying it. Okay, so that we talked about, that's why it was called millimeters of Hg. That was the tradition for a while. And then this guy, I don't actually remember what Torr's deal was, but then we have Pascal. No, I guess there was Torr. And then we have some, I think there are other people we don't talk about anymore. But Pascal and Torr were both scientists. There was another guy too. He didn't get a name. And then, so there were so many competing ways to talk about pressure. Pascal and kilopascal is the same thing. It's just 1 is times 1,000. That finally people are like, oh my God, we have to have a standard way to talk about the gases. The most gases you come into contact are in the atmosphere. So we're just going to call it an atmosphere. So the amount of gas in the atmosphere at sea level is considered standard temperature and pressure, and that is we're going to call that 1 atmosphere. If you go up in the atmosphere, there's less molecules in the atmosphere, and so then they spread out more, so there's less density because there's less stuff there. And by the way, why does it not get hotter as you move up? Because you're getting closer to the sun? It's literally because there's less molecules to absorb sunlight and then release heat, okay? And so, what was the point? Okay, as you move up in altitude, you get a decrease in atmospheric pressure, so you go less than 1 atmosphere. As you go underwater or go down towards the center of the earth, you get a whole lot more pressure, because there's literally molecules on top of you and they're squishing you, okay? So the reason why we haven't been able to dig very deep into the earth, in comparison to the size of the earth, is because there's so much heat and pressure as you move down through the earth, because there's just so many molecules pushing on each other. It gets so hot that our drills melt. And it takes so long just to get down there with one working drill, and then it melts, and then you have to pull it back up, and by the time you get the next drill down there, it's also melted. So there's a limit to how far we can go based on the materials we use. Beep, boop, boo. Okay, so ATM is the standard we use now, but you still see people report in torr or in kilopascals, whatever. Just make sure you memorize 1 atmosphere is the same thing as 760 torr, which is the same thing as 760 millimeters of mercury, which tells you that Torr just decided, I'm gonna name it after me now. But it's nice, just remember 760, okay? Also remember 101.325. Think about it like a radio station or something, okay? So these are the 2 numbers you definitely have to memorize. Each one of these is equal to 1 atmosphere. And so anytime you see, and we'll see. So the problem is you have to make sure your units match. If you're doing gas law problems where you have a before and an after situation, you can't compare. It's like comparing apples and Oreos, right? You can't say, it's like a bad trade. Like, hey, I'll give you an apple for your Oreo. I mean, if you're into health food, maybe you like that. But, if you're a little kid on the playground, absolutely not. I'm keeping my Oreos. So you have to make them even in order to compare their math, right? Okay, so memorize these. Make sure, basically it's very easy because anytime you see 760, anything in torr, just divide by 760. If you see anything in kilopascals, divide by 101.325. All right. So you may look at these gas laws and be like, oh my God, I have to memorize so many. No, just memorize the combined gas law. It's so much easier. PV over T equals PV over T. And this is saying when you look at a gas, you can figure out its pressure, its temperature, its pressure, its volume, and its temperature. And then you do something to it and remeasure. That's all gas law problems do, okay? So the idea is if you have this problem, okay, and helium balloon is filled to a volume of 500 millimeters at 30 degrees Celsius and has a pressure of 800 millimeters of mercury. What volume in liters will it have? Oh, I did not answer the question properly. What volume in oh no, I did. Okay. Liters will it have at 0.9 atmospheres and 285 Kelvin? So immediately I'm like, this is a before and after problem because they have more than one pressure, volume, or temperature. So it's a before and an after problem, okay? So before anything happens, because we have a balloon filled with a volume of this at this with this, okay? So before, I have my pressure is 800 millimeters of mercury, my volume is 500 milliliters, and my temperature is this, okay? Cool. Except not really, because it's easier just to deal with everything in atmospheres. You could deal with it in millimeters of mercury if you want to multiply this by 760 instead of dividing this by 760. It's just easier to get in the habit of making sure everything's in atmospheres, though. Okay, so again, what I did is I divided 800 by 760 because 1 atmosphere is equal to 760 millimeters of mercury. Okay. What I should have done in this problem is I should have checked, because you want it to be in liters. I'll do it at the end. So I should have divided this by 1,000 to be liters, because then I would get liters at the end. And because of the problem with temperature scales, we have to use, when we do gas laws, we have to use what's called Kelvin. So the Kelvin scale is all about kinetic molecular theory, because the idea being, if there's a state when all molecular motion stops, we'll call that temperature 0. The problem with using Celsius and Fahrenheit, who are named after 2 British dudes, I think, is that they say, okay, so Celsius was developed to deal with water. So 0 Celsius is when water freezes. 100 Celsius is when water boils. Awesome. Except that means that you could, in theory, if this T is 0, you're dividing by 0, and that's impossible. So that you can't use that. Fahrenheit, on the other hand, is, and remember this was developed by an English lord in the 1700s. Fahrenheit is supposed to be at 0 degrees Fahrenheit, humans die, and at 100 degrees Fahrenheit, humans die. Now, we know as people who live in LA, we can actually survive at 100 degrees. It just sucks. But, and maybe if you're someone like me, the idea of anything under 40 degrees is horrifying, right? But again, we have this scale where there's a 0, and so we don't want that 0 if we're dealing with the math where temperature's on the bottom, okay? So, okay. I was just about to say there's a way we could fix this by just flipping them, but whatever. This is what was set up. One way to remember this is pivot. Oh, we're all so tired of that word. But the idea is it's PV and then you pivot to the T. So PV over T equals PV over T, where you have a before and an after. So before is 1 and after is 2. That's how I have always remembered it. I always really liked gas laws because they're so much easier than stoichiometry. So if I go through all my conversions so that the before units match my after units, I see that I'm going to divide the millimeters of mercury by 760 and get 1.05 atmospheres. Cool, these two match. 500 milliliters, well, I'm looking for volume, so that's over here. And then I'm going to add 273 to convert to Kelvin. This is already in Kelvin, so I'm happy. So now I can plug into PV over T. And the reason why I say you do not have to memorize all 3 of these, just memorize this, is because if you have a problem like, here we go. So this has liters, temperature, pressure. So that's not what I want. If you have a problem, pressure, volume. If you have a problem like this, where, okay, I could set it up for PV equals PV over T equals PV over T. I've got volume, I've got pressure, I've got pressure. Oh, I don't have temperature. Cool, then you just leave it out of the equation, okay? So by just memorizing PV over T, you just leave out whatever isn't in the problem. So I've always just memorized this. Who cares who came up with it, which law? If you get tested on that, that is nonsense and you need to fight it because that is not as important. It's interesting if you're into scientific history, but it's not as important as knowing how to manipulate the equations. Okay, so then we just plug and chug. Okay, so just make sure you keep all of the 1s together and all the 2s together. So PV over T, so this times this divided by this equals this times X, because that's what we're looking for, divided by this. Math happens. No, because this was in milliliters, my answer is going to be in milliliters, but I need to divide by 1,000 milliliters per liter so that we end up in liters. Because I did not read the problem carefully enough, and it asks for liters. So 547.8 milliliters divided by 1,000 is going to give you 0.5478 liters, and that is your final answer. All right, cool. Hopefully this makes sense. I love gas law problems. It's literally plug and chug. Just make sure you keep in mind what happened before and what happened after. The only way to make these problems complicated is if they make the language complicated. So, for example, they could say, a gas was at 14 degrees and suddenly jumped to 25 degrees. If the pressure was first this and the volume was this. So, like, they don't separate out what before and after is. Just make sure you read it carefully, okay? They do tell you, you just have to be good at reading a problem. You're good at reading a problem. You'll do well. Okay, so also make sure this makes sense. So the idea is, okay, if pressure went down. So if pressure went down, it's like you have a balloon and you let it up so that it can fill up more. So volume should increase. So I should have something higher than 500. Oh, I have something higher. Then I did this right because I did get something higher than 500. If you get something lower than 500, you maybe didn't divide where you should have, something like that. So be careful. All right. So the ideal gas law, then remember, this is saying that gas molecules don't react with anything. They move in a straight line, and they act exactly the same way at any temperature and pressure, okay? So this is looking at one gas at one temperature in order to figure out one part of it. And there's actually 3 equations you have to memorize here. When I was in high school and college, we only cared about this one. But I think your teacher worked with these things when she was in grad school, so it makes sense she would have more. So the one to remember is PIVNERT. Sounds like pervert, sort of, so it's easy to remember. PV equals nRT. PIVNERT, PIVNERT, PIVNERT. PIVNERT is like Brinkelhoff in that it's a fun chemistry word that you can remember forever. Okay, so PIVNERT. It's literally, so what's P? Can only be pressure. What's V? Volume. N is number of moles. That's how I remember it. It's just they ran out of stuff. It can't be M because that's mass. And so instead of, in order for this to work, this has to be moles. And so it's like, I like to think of it as the number of moles, to remember that N is number of moles. R is a constant that, again, you have to memorize. Maybe I'll go through and highlight all the stuff you should memorize. I'll just say, memorize. Okay. And there's actually a lot of different forms of R based on if, which kind of pressure you're using. So you're kind of given a break here in that if you're told to just always use atmospheres, you only have to memorize one kind of R, okay? So, yay, that's good. Also remember that the what R tells you is what all the units everything has to be in, because it has to cancel out to be nothing. So it tells you that your volume must be in liters, your pressure has to be in atmospheres, your N has to be moles, number of moles, and then K is your temperature, okay? So temperature is in, okay. So there's also a couple more things you can do. So molar mass, remember, comes from the periodic table. From periodic table. Okay. And if it's like O2 for oxygen, remember your Brinkelhoff gases are always in pairs. That's another way they can trick you. I put that on the stoichiometry notes. So remember that so M for molar mass is from the periodic table. So oxygen, if it's oxygen gas, that's O2. Okay, any of the Brinkelhoffs are going to be 2. So 2 BRs, 2 Is, 2 Ns, 2 Cls, 2 Hs, 2 Os, 2 Fs. So you would just take oxygen's molecular mass, which is 15.999 or 16.0, and multiply by 2. That's it. That's your molar mass. Okay, same thing as molecular mass. Mass is in grams, which makes sense because the molar mass is in grams per mole. Okay, and then density is always in grams per liter. Okay, and remember, density is how much space something takes up. Remember that gases, the more energy they have, the more space they take up. Density isn't how much space something takes up. That's volume. Density is how much stuff is in a certain space. Okay, so the more energetic your gas particles are, the lower your density should be, because there's literally less grams in the same number of liters. Okay, so the problem you have here, what volume will 8.47 kilograms of sulfur dioxide, which I gave you, but remember if you have sulfur, S, and then di means 2, and then oxide means oxygen, so sulfur dioxide is SO2. How much volume does this gas occupy at a pressure of 89.4 kilopascals and a temperature of 40? Now, here's what you do. You just list out your variables. PV equals nRT. PV equals nRT. Make a little song. Make a dance. I don't know. Just remember, PV equals nRT. R equals 0.0821. I don't know. How do you remember these two? I don't have a good way to remember this, but I like to remember this as dinosaurs. How did I put it? This was dinosaurs, multiple personalities, really tough. That's how I remember. Density is MP over RT. MP is also a British term, and then, I don't know, make something up. Whatever works for you. Even if it's a dirty thing, you don't have to tell anyone as long as it helps you remember. Okay? So, in this problem, I'm just going to list out everything I have in the problem, okay? I want it to be PV equals nRT. I'm going to start with P and V, because all of the problems involve PV, or at least involve P, right? So here's P, and then I'm going to figure out, is this a gas law problem where I have before and after, or is this a PIV-NERT ideal gas law problem where I just am solving for at one condition? Okay, so I have P is 89.4 kilopascals. That's a problem. I need it to be in atmospheres. Just divide it by 101.325. Okay, remember that's one of the things you memorize. Okay, because 1 atmosphere is 101.325 kilopascals. So pressure is actually 0.88 atmospheres. Volume is what we're looking for. It must be in liters, but it will end up in liters. N, oh no, we don't have N. N is number of moles. We have kilograms. Ah, dang it. So we have to take the, remember to find moles, you take the grams given and you divide by the periodic table numbers, right? So we don't have grams, so the very first thing I have to do is to take this kilograms. There's 1,000 grams in 1 kilogram, so I'm going to multiply kilograms by 1,000. It makes sense to multiply because a kilogram is, 1 kilogram is 1,000 grams, so there should be a whole lot more grams than kilograms. So the units cancel properly. And then I'm going to divide by the molecular mass, because that's how you get moles, right? So I take the number of kilograms given, multiply by 1,000, divide by the molar mass, and I get 132.2 moles. Oh, that's so many moles, Miss Knoll. I know, it's kilograms. It should be a whole lot of moles. Okay, R is always 0.0821, 0.0821, 0.0821, 0.0821. That's what you should memorize. Just memorize me saying it. It's so fun. And T is in Celsius, which remember that it could go down to 0 and you can't divide by 0. And in this situation, you'd be dividing by 0. Oh no. So in gases, we always deal in Kelvin. So if you see C, add 273. Ooh, that's the way to remember. If you see C, add 273. Make it a song. Make it a TikTok. Am I patronizing saying that? A little bit. Okay, and then so I have everything from the problem has been written, and so that is nicely just PV equals nRT, right? So PV equals nRT, plug it in, chug, 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 you get your answer, okay? Done, that's it. If you forget if you're supposed to be in liters or milliliters, remember, just look at the unit for 0.0821, okay? It's liters, so this must end up in liters. Okay, cool. So let's do one more. So the density of dry air, which means there's no water vapor in it, at 27 degrees Celsius. Oh no, C, add 273. You see a C, add 273. And 750 millimeters of mercury. No, atmospheres, divide by 760. Is 1.162 grams per liter. Cool, that's density. That means I have to use my dinosaurs. D equals MP over RT. Dinosaurs, multiple personalities, really tough. Okay, so I'm going to use that because I see density and I'm like, I got to use that one. None of the other ones use density, so I really hope this works out. Oh, it will. It's going to be fabulous, okay? Because I want to find the molar mass, okay? So if I use D equals MP over RT, you'll see I wrote them out that way. So D, MP, RT. Okay, so D is density, gives it to us. M is molar mass. We don't know it. That's what we're looking for. because air is a combination of many gases. Sometimes people forget that. We talk about breathing air. We do take in anything that's in the air into our lungs, including ash during wildfire season, which is a global warming issue. Let's just cry about it after this test. So whenever you take in anything that's in the atmosphere, we actually only use the oxygen. Okay, that's it. Which is weird because our atmosphere is 72% nitrogen. So evolution is an example of something that doesn't not work. It would make more sense to use nitrogen because there's a lot more of it. But remember, nitrogen makes 3 bonds. And so it's a lot harder to cause nitrogen to bond and unbond than it does is oxygen, where they have 2 bonds and then 2 little lone pairs on the edge too that are just ready to rip things up. Remember, oxygen's a bit of a bastard. Okay, pressure is, again, it's in millimeters of mercury. Millimeters of mercury. Divide by 760 to get to atmospheres. Okay. R is 0.0821. I don't remember how I sang it a second ago. 0.0821. 0.0821. Smush it in your brain. And then temperature, oh, I see a C. I better add 273. Y'all, I'm so funny when I haven't slept in 3 days. Okay, so that means that our temperature must be 27 plus 273 or 300. Very nice. So remember, dinosaurs, multiple personalities, really tough. That's my equation, D equals MP over RT. So then I just plug it in. I've set this up perfectly, so I just plug straight in. That's why I like to do it this way. I'm efficient. Lazy is another way to say it, but you know what? Efficient. Okay, so I just plug it in. X is the volume that I'm molar mass is what I'm looking for. So I've got my molar mass times my pressure, and I'm dividing by my R and my volume. Please use your parentheses. Please use your parentheses. If you put this in your calculator as 9.87 divided by 0.0821 times 300, it's going to multiply the whole thing by 300 instead of just the denominator, and you're going to get the wrong answer, and you're going to be very sad, and I can't handle your tears. Can't handle it. Okay, so please make sure that you use your parentheses very carefully in your calculator. That's why you have them. Okay, so set it up, do some math, boom, the answer is 29 grams per mole. Easy peasy. You just gotta set it up right, and then you get your answer, and it's beautiful, and then you pass chemistry, and then you're so happy, you cry happy tears, and those tears I can deal with. Okay, y'all, I love you very much. I will send you the answer key to the rest of these soon, probably before I go to bed tonight, maybe, if not, early tomorrow. And you're beautiful and wonderful, and never forget it, no matter what happens, your worth is based more than a test grade. You're perfect, don't forget. Bye!